Welcome to MAT 307 Numerical Analysis class. In this lecture, we are going to introduce and exemplify Gaussian and Gauss-Jordan eliminations. Both of these approaches are to solve system of linear equations. Gauss elimination is a method for solving a system of linear equations. The main idea is to apply successive elementary row operations to the augmented matrix to obtain its row equivalent echelon form. Then, using back substitution, we can find each unknown. Okay, so Gaussian elimination is an approach to solve system of linear equations. And doing that will basically employ elementary row operations successively, and then we will obtain row equivalent echelon form to the original augmented matrix. And then we know equivalent matrices have the same solutions. Okay, so using this fact, we'll say the solution to the row equivalent echelon form will be the solution to the original system, and then we will basically get the solution easily. Okay, so an example, consider the following linear system. So this is the linear system we are given. Without using a systematic approach like Gaussian elimination, if you're given such equation, our intuitive approach will be to eliminate unknowns from the equations, right? And then doing so, if you're not systematical enough, then you'll maybe eliminate one unknown from the equations, but while doing so, you will introduce the other equation again, other unknown to the equation. Okay, so this elimination has to be systematical. Otherwise, you're always doing lots of operations, but you're not basically getting anywhere. Okay, so one systematical approach will be to employ Gaussian elimination, and this is not the only approach. Okay, so you can introduce row echelon form in, for example, other way around, like you can introduce the echelon form as, for example, having all the zero entries on the top, and then instead of having the leading entries on the right of one above, you can make it the leading entries are on the right of one below, for example, and say this is my new echelon form. Okay, and you don't have to call it echelon form, but you can call something else, and then you can still get similar approaches to solve linear system. But this is Gaussian elimination is one of the elegant way to solve system of linear equations, and also it is very common. And if you say Gaussian elimination anywhere, people knows what you're meaning. Okay, so this elimination, this approach will make the process of solving a system of linear equations convenient and also universal. Okay, so an example will be here, and here in this example we need to first introduce the augmented matrix for this equation, and then we are there. Okay, so this is our augmented matrix, and then here we need to apply successive elementary row operations to get its row equivalent echelon matrix. Okay, so we need to get an echelon matrix. Okay, to that end, we need to eliminate these entries and make them 0. So, okay, how can we do this? We can basically multiply the first row by 2 and then subtract from the second row. And we can add the first row to the third row. And also, we can multiply the first row by 2 and then subtract from the last row. Okay, so they are listed here. And when we do that, we will have zeros below the leading entry of the first row. Okay, and also the entries, other entries will also change because if you perform the first operation here, first operation in the second row, this is twice the first row will be subtracted from the second row, so this will be 0, and then this will be 2, 5 minus 2 will be 3, and this will be -2, -3 minus -2 will be -1, which is here, and this is 6 minus 4, and this will be 2, and we have to have 9 minus 10, and that's gonna be 11. Sorry, -1. Okay, so this is what we really get, and also you can do the same operations on the second and last row, and you'll see we end up with these entries. Okay, so once we're at this point, we're getting the echelon form, right, in the first column. If you check the first column, we have the leading entry, below it they are all zero. Okay, we have to take care of the second row and also the second column. Here we have 3, and then we need to subtract twice the second row from the third row, and also 3 times the second row from the last row in order to obtain zeros here. Okay, so once we apply these operations, we get zeros below the leading entries or leading entry of the second row, and this will quite look like the row reduced, sorry, row echelon form. Okay, so this is like reduced echelon form, and we also need to move on and do the same thing for the third column. Okay, so the leading entry of the third column is -1. We need to eliminate the entries below, right? So we can do that by adding the third row to the fourth row. When we do that, this will be 0, and this will be 2, and this will be 6, 0 to 6, and we obtain 0 here. Okay, now let's check the matrix. This matrix is in row echelon form because, as you see, this is the leading entry, and below it they are all zeros, and this is 3, which is the leading entry of the second row, and below it they are all zeros, and -1 below it zeros, and all the leading entries are moving to the left while we are moving from first rows to the second rows and so on. So this is really an echelon form. So now we can use back substitution to get unknowns. Okay, so we know we just applied we applied elementary row operations. So the solutions to this augmented matrix and the original system, the augmented matrix of the original system will be the same. Okay, so because they are equivalent. Okay, now if we go back to the system of equations, we will get this one. Okay, and here we can apply back substitutions. Like here we have 2 times x4 will be 6, so x4 will be 3 basically. Okay, x4 will be 3, and given x4 equals 3, we can say this is 12, and 11 minus 12 will be -1, so x3 will be 1. x3 is equal to 1, and then x3 equals 1, and x4 being 3 makes this 6, minus 1 will be 5, and then moving 5 to the other side, this will be -6, and x2 will be -2. x2 is -2, and here we have x2 -2, and -1, -3, +6, +3. If we move +3 to the other side, 5 minus 3 will be 2, and x1 will be 1. So this is what we get. Okay, it seems like Gaussian elimination is an elegant way to get solutions, and it gives the solutions immediately, like we've done in this example. Okay, so next we move on to the Gauss-Jordan elimination, and this is also a method for solving a system of linear equations. The main idea is to apply successive elementary row operations to the augmented matrix to obtain its row reduced echelon form. Okay, so this time we have row reduced echelon form instead. Then using back substitution we can find each unknown. Okay, so again we consider the given example. Okay, so this is our linear system. Okay, we need to put this linear system into its augmented matrix form. Okay, so this will be the matrix we will be working on. And we need to apply successive elementary row operations on this matrix. Okay, in the first row, we have the leading entry is 1, so which is nice because we just need to have 1 here already. So if that wasn't 1, we needed to divide the whole whole row by what we have here, and then we would get 1 here. But in this particular case, we already have 1, so we can proceed with that. And also here we have 0, which is also nice because we are trying to make this entry 0, so it is already 0, so we don't have to worry about the second row at this point. And here we have -3, so that means we have to add 3 times the first row to the third row. And also we have 2 in the last row, fourth row, so that means we have to multiply the first row by 2 and then subtract the resulting vector from the last row. This is also a vector. Okay, so they are listed here, and when we do that we will have 1 here and 0 below. Okay, so this is what we really need to have in the first column if you're moving on to the row reduced echelon form. Okay, so in the next row we have -3 is the leading entry, but I'll do some manipulations here because it seems like we have -1 there. Okay, so intuitively if we interchange the second row with the third row, we can get the -1 here, and also multiplying this -1 by the whole row by -1, then we can basically have 1. Okay, so instead of dividing the second row by -3, okay, and working with fractions, I'll basically interchange rows and proceed with that. This will make my computations easier. Okay, so I did that, so I multiplied the last row by -4 and then interchange the last row with the second row. Okay, so I ended up with this. Okay, here we have 1, which is nice, and also we basically make it 1. So we use this 1 to eliminate all the other entries on its own column. Okay, so because in the row reduced echelon form, the leading entry is the only non-zero entry on that column. Okay, so this one will remain and this other entries will be 0. To make them 0, I need to multiply the second row by 2 and then subtract the result from the first row, and also multiply by 5 and then subtract the result from the third row, and also multiply by 3 and add the resulting vector to the last row. Okay, so this is what we have listed for these operations, and then when we perform all of these operations we will get 0 on the first on the second column first row, and here we also have zeros below the leading entry of the second column, second row, sorry. Okay, so this is what we really need to have already if you're moving on to the row reduced echelon form. Okay, so the next step will be to make this leading entry 1. To that end, we can divide the third row by 34. This is basically means we multiply the third row by 1 over 34. Okay, when we do that, actually here I also have one more operation, and I say I can divide the last row by negative 1 over 22 to make it 1. It seems like unnecessary operations, but if it will make your life easier, you can do this sort of operations while you're applying one operation if you to the matrix already. So this is something you're allowed to do because we're moving on to the row reduced echelon form, and it's unique. Even if you do that, you'll still get the same result. Okay, so this is 34. So we divide the third row by 34, and this will be 1. And here we also have 1. Okay, so they are ones. Okay, now this leading entry has to be the only non-zero entry on its own column. So this 13 has to be 0, and negative 8 has to be 0, and this has to be 0. So to that end, we can add negative 3, negative 13 times the third row to the first row, and also we can add 8 times the third row to the second row, and also we can subtract the third row from the fourth row. Okay, so when we do that, you'll see we have zeros here, and also the other entries will change as well, just like we did before. Okay, now if we check the first 3 columns, you'll see it is getting there. It is it's looking like row reduced echelon form already, but we have extra columns here and also row, so we need to perform the elementary row operations there as well. So next we need to make this entry, this leading entry, to be 1. So to that end, we can multiply this entry by negative 187 divided by 42. Okay, so when we do that, we will have this column, this row, sorry. So this will be 1. Okay, and also we need to eliminate all the other entries on this column, on the fourth column, because the leading entry must be the only non-zero entry on its row on its column. So all of these has to be 0. So to make them 0, we can basically multiply the fourth row by 5 over 34 and add the resulting vector to the first row, and also multiply the fourth row by 5 over 17 and then add the result to the second row, and lastly we multiply the last row, the fourth row, by negative 3 over 34, and then basically subtract the result from the third row. Okay, when we do that, we will see this is 1 and zeros above. Okay, so now let's check the matrix. This augmented matrix is indeed row reduced echelon form. Okay, because as you see, the leading entries are the only non-zero entries on their own columns, and it is also in the row echelon form, and also the leading entries are 1. So this is what we really need to do. So this is what is required to be row reduced echelon form. So this is row reduced echelon form. So from this point on, we say this is an equivalent form. This is an equivalent matrix to the original augmented matrix. So their solutions will be the same. So okay, so if we move on to the back substitution, we basically get these equations. Okay, so these equations will give us the solutions immediately. So x4 will be -2, and x3 will be -1, and x2 will be -2, and x1 will be -1. Okay, so this is the solution. Some comments on this approaches. First, Gaussian eliminations and Gauss-Jordan eliminations. First, if we consider both of these approaches, Gaussian eliminations was quite straightforward. Then we jumped onto the back substitutions immediately. But Gauss-Jordan elimination uh, gives us the solutions on its final stage, and back substitution is not involved much. But in this particular case, we have to do lots of elementary row operations. Okay, given a matrix or system of linear equations with lots of unknowns, say 10,000 unknowns. If you move on to the Gauss-Jordan eliminations, this means you're adding or subtracting a vector of 10,000 entries to the other row, okay, other vector. So this means lots of operations, okay, and lots of unnecessary operations if you're performing the same thing with Gaussian elimination, okay. So seems like Gaussian elimination is a better approach. Better is in quotient mark. So it's better approach in terms of getting in terms of having less computations. Okay, but Gauss-Jordan elimination is an approach to find the inverse of a matrix. So it is very useful when we are trying to find the inverse of a matrix. So it is like they have their own duties. If you're just solving the linear system of linear equations, then go with the Gaussian elimination and make life easier for yourself. But if you're trying to find the inverse of a matrix, then you have to go with the Gauss-Jordan elimination, and we will get to that point uh, at some point in this course. Okay, so this will conclude my lecture here. Okay, thanks for watching and listening carefully. See you next time. Bye.